concept for today is the idea of chronoamperometry. So we just talked about what happens with constant potential amperometry if you just hold at a flat voltage. The only difference in chronoamperometry is now we're going to do a step. So we're still not, there's no ramps, but we're going to step from some sort of lower voltage up to a higher voltage. That's the basic idea of chronoamperometry. So it's a potential step experiment. I should label my axes. So it's a potential step experiment. Now, I once had a collaborator of mine who was a biologist say, you electrochemists make everything so complicated. You have about 100 different names for techniques, and they really all come under about 2 concepts. And he is absolutely right. So when you get to potential step techniques, there are a gazillion names for things. And they're all a slight variation on something else. So if you think about stepping, you could do one step, but that's not actually what people do. They tend to do steps either like this, right, where you're kind of stepping up. And if you were to first design the experiment, you might think that looks like a good pattern. I'll step to a little bit higher thing every time. But there's some problems with that, which we'll get into. And so then you say, well, maybe it would be better to keep the step height the same and, only not go back to the, holding potential each time. And now we'll do this. This is more, as I said, often called differential pulse versus chronoamp, et cetera, et cetera. But so you'll see these concepts, and it really just has to do with how they exactly do it. And then there's square wave, which is very similar as well. So don't let the names trip you up. The concepts are about all the same. Whether you, go back to baseline, whether you, sequentially go up with the same step height, et cetera, et cetera. But these techniques have been around for a while, and they have a lot of good conceptual things to them, and they're pretty easy to do. Okay, so let's go back to my original just one step. These are too complicated. Once we know what happens on one step, we can just assume it happens on all the rest of the steps, right? So we're going to go back to one step. So what happens when I step from a lower potential to a higher potential? Well, we've learned about background current, right? So if I'm going to talk about background, right, I know that as soon as I step up, if I do this right, I can line these up in time. I didn't do it right. So let's do a graph of, again, background, charging current versus time. And again, I'm going to dot this down. All right. So background charging current versus time, right? And I'm going to be holding at some sort of low level. And as soon as I step up, right, I will cause those ions to rearrange, and it will come, let's do it this way. It'll come back down, right? And this, again, is an exponential decay on the background charging current. Great. So that's what's going to happen. Same thing, let's just assume that I'm going to step from a potential that we can't oxidize the molecule to a potential we can. All right, so I'm going to put that little assumption in there for my graphing purposes. So we're going to now make a graph of Faradaic current, so that's the electron transfer to my analyte, versus time. And again, it's going to probably be low or 0. And then it's going to, all of a sudden, again, we're not going to stir right now. That would be too complicated. Just assume a thing. We're going to get this to come back up. And now it, too, is going to decay back down. And it's going to decay, as I said, oops, no E there. It's going to decay with a t to the minus 1/2, a square root of t kind of decay. I tried to draw them. Let me switch colors here. So I'm gonna put them on here so you can see. It turns out that the t to the minus 1/2 decays slower. I told you we would need to know that, the electrochemists, and that actually helps our cause tremendously in chronoamperometry. Because the problem is with this, so I'm gonna step up here. If I measure right here, a lot of my current, right, is gonna be due to background. So I'm going to get some Faradaic current, and I happen to draw them on the same scale here, which was really bad of me. If I really wanted to draw them more to scale, it would be like background, And then Faradaic, right? Faradaic, it does not rival background current, right? Background current, you've got tons of ions, they're moving around. Your concentration, your analyte and biological electrochemistry is probably small, right? And so, you don't want this to be, the main signal. And so what people do is usually wait a little bit. And so when they actually sample in chronoamperometry, they tend to sample at the end of the step. And so if we were to sample at the end of the step in my drawing down here, you would see by that point in time, hopefully most of my background current has decreased, but I still, because the t to minus 1/2 doesn't go down as much, would have a little bit more, there. And so that way I would try and minimize the background charging current while getting still some Faradaic current. And so people play with the times on these, right? You wait too long, you wait 5 seconds, and they're both going to be down here at 0, right? So there's kind of like this optimization of I want the background to be going down, I want my Faradaic current to still be there, a lot of parameterization, that kind of thing. One of the reasons this is a better technique is that every time you have the steps being the same, you should get approximately the same background on those steps. Here, the problem is you'll get a lower background, like stepping this big step compared to this small step, you get a lot more background current here than you would here. So here, because the size of the step is about the same, the background current, the contribution should be about the same. And so when we're doing this, again, we're getting bunches of little steps, so we would be measuring here, and here, and here, and here. And so when we do that, if we plot current versus, potential. And potential here is going to be whatever the potential of the step is, right? And you'll get a curve. I'm going to do it in dots first, because that's what you actually get. That's the data you get. It's not continuous. It's steps, right? And then, because we have computers and software, we'd fill in, poorly. We'd fill in. Computer would do it better than I just connected the dots. You connect the dots, right? But it's dots. It's not a continuous curve, right? And so you get dots, right, on that curve. So people in biological electrochemistry like DPV, because DPV tends to give you narrower peaks than CV. And that's because you're stepping to those discrete things where you can do, like say, all the electrochemistry and come back, all the electrochemistry and come back. And so people tend to, the peak width here tends to be narrower. So if you wanted to claim you could see 3 things, right, and you want to fit them in, that window, that biological window I told you that we're limited by, sure, narrower peaks could be good, right? So people like this, and my personal least favorite papers out there are ones that look at dopamine, uric acid, and ascorbic acid, but that's been done about 1 million times with using DPV, right? Because with CV, those peaks tend to be kind of wider, difficult to do, but with DPV, they tend to be narrower. So there you go. So narrower peaks than CV. And so, but the consequence of this, and by the way, if you wanted to reduce, you could, my drawing level will not be up to maybe coming back down. You just come back down. Right, so if you want to like the reduction, you can come on back down on your steps, right? So you can get that, or this is the example of just like what it would look like for an oxidation. So people have used this. The obvious disadvantage is all this time spent stepping and going back down, stepping and going back down, even if these are only, 100 milliseconds or, that kind of thing, if you're trying to do it in a faster way, is that often this whole thing, it's not impossible for it to take something like 10 seconds. You could go even slower, but and so you can go a little faster, depending on how much you want to go up and down and what you want your step size to be, et cetera, et cetera. It's hard for me to put a parameter on it. But 10 seconds is, not unreasonable, right? And so that is not the time scale we typically do fast scan CV. You can see why people say, oh, but I want to go a little faster. But on the other hand, you can get a narrower thing. Again, you don't get really good identification with chronoamperometry or DPV. Sometimes people will, if they go back down, do an ox to red ratio to try and so how much oxidation peak versus reduction peak. For dopamine, this number usually ends up being somewhere between 0.6 and 0.8. You can already see that that's not super precise. It's like, oh, the number's going to be between 0 and 1, and I just gave you 0.2 range. That people, when they do it, they're like, ah, yeah, good enough. That's the range for it goes. There aren't a lot of people right now doing actual in vivo chronoamp, but the one group that really is Lynn Dawes' group, who is studying serotonin. So people in this lab have read a lot of the papers of hers, and she's got Lynette, okay, Dawes' group, and so we've got, she's got a chronoamp setup which she's using for serotonin pretty successfully. And again, if there's rules to biological electrochemistry of knowing what you're looking at, and none of our techniques are that great at selectivity, but if you know what brain region you're in, you're selectively stimulating only certain neurons, et cetera, it can be pretty good. And she's done a lot of mechanisms of serotonin transporters and that kind of thing with chronoamperometry. A guy named Greg Gerhardt kind of pioneered a lot of this, but honestly, I think most of it's fallen out of favor with the fast scan techniques just being a little bit easier and a little bit more prominent. So it's not that you can't learn it, but if you go back to fundamental electrochemistry, it's there all the time, right? I would just, it's, papers where people are doing electrode development, papers where people are learning about fundamentals or properties or that kind of thing. As I said, separating things, it's there all the time.